Hi class, it's Bill Berry back with another presentation for week 9 of our Java 2 class. This week we started with complexity notation. There's a video on that. We looked into what big O, big theta, and big omega mean, and hopefully that cleared up some things and gave us some more precise terminology and understanding of what those things mean mathematically. And now we're going on to look at two recursive sort methods. So the two that we're going to study here are the merge sort and the quicksort. We'll be interested to apply what we just learned in the last video, which is what are the properties in terms of time and space complexity of these. How are these different from the simple methods that we learned before that were more iterative in nature? So there are two we're going to look at. As I said, the first is going to be the merge sort. So don't try to read this slide. I should just actually blank it out for a second. But think about it for a second. If I have as a teacher two stacks of papers, each one is an assignment that, let's say, somebody wrote a little quiz in class or something. I have two stacks of papers and I have alphabetized each of them because as I graded them, I recorded the grades in alphabetical order. But if you think about it, some people will not have been here the day that we gave the quiz, so there are going to be some gaps in those papers. And the people who weren't here for the one quiz might be different than the people who weren't in class for the second quiz. So it's not that they are identical in terms of matching up name by name. They're going to be different. So if I have these two stacks of papers and I want to merge them into one stack to give back in class, how do I do it? Well, I put them down face up and I find the smallest name in either one. So maybe I have someone Alarcón, an A on the first stack, and on the second stack I have Barajas. Well, Alarcón, A starts with a lower letter, so I'm going to pick up the A and turn it face down onto the other side of the desk. Then I'm going to look and see in maybe the one on the right, maybe Barajas is in fact the smallest one, but I just uncovered one on the left. So maybe Baca, B-A-C-A, comes before Barajas, so maybe I again pick one out of the first stack and put it face down on the other side of the desk. Then again, I look at the two and I just take whichever one is smaller. So notice that what I'm not necessarily doing is alternating. I'm just looking at both of them, finding the smaller of the two, however it is you're considering small, and picking up that one and putting it aside. And I continue that until I'm done. One of the interesting things, though, about while I'm not done is what if I exhaust one pile entirely? What if I take the last paper out of pile number 1? What can I do with pile number 2? Well, I can just take the whole pile and turn it right over onto the desk. I don't even have to look anymore. I know they were already alphabetized. I know that they must come after the one that I picked up off the other pile, so I can literally turn over the whole other pile. So that's an interesting little thing which will give us a little bit of efficiency, which is kind of good. Now, how are we doing this with an algorithm, with a sorting algorithm? Well, you have two steps here. You're going to do this dividing. You're going to divide all of the elements into equal halves, and then you're going to keep dividing recursively down and down and down until you have stacks of 1. And then you're going to apply this idea of looking at the two and picking the smaller one and then picking up the other one. In each case, you're going to come back up and merge them together. So you have this division concept that happens on the way down, and then on the way back up, you're going to merge those things together as you go. And so you get this recursive breakdown and recursive remerging, and eventually it's all done. So hopefully that makes some sense to you. Now, let's see, what else do we want to talk about here? One thing that's interesting is you're going to have extra space. This is one algorithm where when you do this merging, you're going to need some extra space. When you put them back together, you're going to pick the smaller of the two, but it's got to go somewhere else. You're not swapping them in place. You actually need to sort of have an extra spot to set it aside. So that's going to mean that there's extra space required. In fact, enough space for every single element to be copied over into this little holding spot. So in the algorithms, when you look at the code, there's always going to be extra array space allocated either on the way in or somewhere in the algorithm. Somewhere there's got to be extra space allocated. So Interesting things about this algorithm. Let's look at the time complexity. We haven't necessarily seen this before. The time complexity, big O, worst case scenario. Notice it's going to be n log n. We haven't seen anything like that with the simple algorithms. How do we do that? How do we accomplish something that is not n squared? Well, you'll notice that n, you're still going to have to look at every number once, right? So n is going to be required. You can't get lower than n. But log n is representing the fact that every time you're working on the problem, you're breaking it down by half. Right? You're always dividing the problem in two. A divide and conquer approach is going to let you have a n log n solution rather than an n squared. Right? Divide and conquer, break down the problem by half. And notice big omega, same thing. Big theta, same thing. So this is a very consistent algorithm in terms of all of its complexities. How about the space complexity? Well, again, here we know this is a little different because we know we need the extra space. So this is going to need extra space. Space complexity is going to be big O of n. Hopefully all that makes sense to you, right? So read that stuff over, pause it, read it. We're going to go through a specific demo with some numbers so that we can see how it works. And this is just a reference slide to give you the overall algorithm, and then we'll do one together to see with real numbers how it would actually work. So let's do that next. All right, so let's say we have these numbers as a starting point. Now I'm going to actually pop out of presentation view here. So I'm going to cancel my presentation so we can actually work in PowerPoint itself. So let me do that real quick. All right, so this is a little more convenient just because I'm going to be dragging around numbers. You'll see a lot of demos on the internet with people using cups. That's a really good way to do this. But in class, you'll see that we tend to use cards. So if we were in physical class together, I would pass out playing cards and you would take one suit and you would use the cards and manipulate those. I find that tactily moving these things around helps to cement some of the algorithm because you see the way that things move around. Feel it in your fingers and in your body a little bit. So let's look at how the merge sort works. The first thing is we have to take and divide the thing into two. Remember that we're going to do this sort of breakdown and then the merge step. So the breakdown says divide the set into two. Now I'm using an evenly divisible set. You don't have to. You could have 5 on this side and 4 on this. It works just the same, not a problem. So I've got to break this down into two. Right, so I'm going to take these set of 4 and I'm just going to kind of move them over a little bit and move them down. And then I'm going to take this set of 4 and I'm going to move them over and down just a little bit here. Okay, so I've now broken that into two and I'm going to recursively do that again. I'm going to recurse to the left side. On the left side, what do I need to do? I need to take this and I need to break this down, and I'll just move it down a little bit to illustrate that I've done that breakdown. And then this, same thing, I'm going to divide this into 2 and divide that into 2. And of course over here I've got to divide this into 2 and I've got to divide this into 2. Okay, so recursively we just did a breakdown. We took the set of 8, we broke it down into 2 sets of 4. Now recursively, I'm not following exactly the recursive pattern because you remember recursion will tend to kind of go all the way down to the left, but you get the idea. Now we still have to do one more. We take this and we recursively break it down, and we're going to keep doing that until we have 2's. So in this case, I'm going to literally end up, I'm going to move these all the way down because now this is sort of the end of our set. Oops, didn't want to make it bigger, just wanted to move it over a little bit. Do the same thing here. I've got to break these down, and these are now going to be somewhere down here, and here's my 2. Now they're still going to conceptually kind of come back in these pairs, right? So I'll leave them sort of close together. This one, we're going to break this down into 2, so let's put that, say, here. This one, say, here. This one here. And last one goes over here. Okay, so we've done the breakdown recursively all the way down to where we have sets of 1. Now we've done the breakdown part. Now we have to do the reassembly part. Now we're actually doing the merging part. So what do? Well, first we're merging just these two. right? In fact, that's the point of breaking it all the way down into one, is so that we can then merge. All we have to do is look at these two and pick the smaller one. Which one's smaller? The 2's smaller. So I have to copy that, or I have to move it into a separate holding place. That's where the extra array comes in, right? We need an extra array to hold this as it comes back. So I'm going to pick the 2 first, and then I'm going to pick the 5 because I just take the whole rest of the stack. I've exhausted this stack. I'm going to pick this one, and there we go, right? In fact, conceptually, sort of, I can actually do this and say, hey, I have that stack, okay? Now here, I'm going to pick the smaller one here. So I'm going to say, yep, 6 is smaller, so I'm going to pick that. And then I've exhausted that stack, so I pick the whole other stack. So in this case, I'm going to pick the 9, okay? So I have this stack now. I want to move it back. Now I need to do something. Yeah, I need to do my ribbons, don't I? Okay. So I want to put that in. I want to put this in the front so that you can see clearly that that's how my stacks are going to be assembled. Okay. Picked up the 2. That's going to be the first in this stack. Picked up the 6. That's the first in this stack. Okay. I picked. Look at these two. The 4 is smaller, so I'm going to copy that into the other memory location. I've exhausted that stack. Now I'm going to bring all the rest of the stack in. There we go. Now I pick the smaller of these two. That's the 3. I pick the whole rest of the stack. Since that stack's exhausted, that's the 8. Perfect. Now I have this set to merge, and I have this set to merge, right? So the recursion is now coming back up with all of the merging. So how do I deal with the merging over here? Well, again, I only need to look at the top card in the stack. I see that the 2 is smaller, so I've got to copy it to some new spot. Okay, so I'll move it to here. What's smaller next? Oh, the 5. Okay, so now I can move the 5 up. And now look, these, I've exhausted this whole stack, so literally I can move this under that card, right? That's going to be a little hard to do with PowerPoint, but I can do it. In fact, I just pick up this whole stack, right? This whole stack just goes under these cards. So I've now gotten myself into a little PowerPoint jam, haven't I? So I'll just do this. There we go. Okay, I just put on my quick steps so that I can put these things together. So now I've got this stack, and now I need to do the same thing with this stack. Which is the smaller? 3 is smaller, so I pick the 3. What's the smallest? The 4, so I pick the 4. I'm going to put this in front. Again, sorry for that. Now I need to pick the smaller. 7 is next. There we go, perfect. We exhausted this stack, take this whole rest of this stack and put it back. And of course now I've got some rearranging to do because I've gotten myself into this bind of having to show you what the stacks would look like. Great. So now I have these two stacks, and my last step to do the final merge, oh, I didn't want to do that. To do the final merge, all I have to do now is take these two stacks and merge them. So again, I need to find which is the smallest. 2 smaller, so I'm going to grab that. Which is next? 3 is the next smallest. Next is 4. Next is 5. Notice sometimes I grab 2 in a row out of this stack. Next is 6. Next is 7. Next is 8. Next is, well, the whole rest of the stack. There we go. So that's how the merge sort works. You divide recursively all the way down till you have stacks of 1. Then on the way back, you merge each of those little pieces back by using the merge step that we talked about. And then recursively, as you're working your way back up the recursive stack, you then combine the next set and the next set, and eventually you're going to combine everything together from the originally 2 divided lists, and now we have 1 sorted list. Hopefully that makes some sense to you. So watch this demo again if you like, or go back and find some other videos that you think. I think the ones with the cups are pretty good. So find some other way if you need to work with this, or lay out the cards on the table yourself. I think that's a great way to learn about this. So that is a quick demo on merge sort. So let me now move this back over. Let's see if there's anything else on the slides that we want to talk about. Nope, that's good enough. Okay, so let us look then very quickly at some of the code that goes with the merge sort and just make sure we see what we were seeing in the algorithm. So here we go, and here is an example of the merge sort. Okay, so in this case, I've got some, in this case, I ask the user to type in some elements. I turn them into integers, so the user gets to type them. That's not the important thing. The important thing here is we do a merge sort. Right? So if we get to the point where we're merging and the list is less than 1 in length, right, or even 1 in length, we're done, right? If the length is less than or equal to 1, we're done. So we just return. But otherwise, we have to do this breakdown step. The breakdown says I need to have a first part and a second part. The first part's going to be half the length, and the second one's going to be whatever's left. Then I'm using here, or again, I didn't write all this code. This is adapted from various internet code. But this code uses an array copy because that's going to do a block copy, which is going to be more efficient than individually copying over the items. So hopefully that makes sense. Just copy a block of memory. So array copy, I've put the syntax here. What's the source array? What position do you want to start in? What's the destination array? And what position do you want it to go to? And what's the length that you want to copy? So we copy over the first part and the second part, right? So we've made, here's this extra space, right? Extra space is going to be here. The original list is called list, but we actually created the extra space by declaring new arrays. And then recursively, I call merge sort on the left half and merge sort on the second half. That's going to call this again and continue breaking it down, breaking it down, breaking it down until you have lists of length 1. And then it's going to merge. So coming back up, it's going to merge the little tiny bits, and then it's going to return to here and merge the next bits and the next bits all the way back up, right? And it's going to merge those together. Well, here's the merge code. What does the merge code look like? Well, hopefully this looks reasonably similar to what we had here. You need to have a way to point to the part that you're working with in the list. You need to walk through that, and you have to figure out where in the list you want to put the items, right? So you're going to either copy the first item, the item from the first list, or you're going to copy the item from the second list, whichever one is smaller, right? So if the first is less than the second, you're going to copy the one from the first list. Otherwise, you're going to copy the one from the second list. And you're going to keep increasing your indexes so that you move forward through the list. And here you're going to keep looping as long as you still got things to process, right? Eventually one of those two lists is going to run out, right? One of these two things is going to be true, but not both together. So one of the lists is eventually going to get exhausted. And then here is another array copy which takes care of the fact that you're going to pick up the whole, quote, the whole remaining stack. Right, so again, if you look at this array copy, you're going to take things from the first list and you're going to put them back in the result. One of these two is going to end up copying 0 elements because one of the lists was exhausted, but this still works perfectly fine, right? If it needs to copy 0 items, then it will not do it. It doesn't need to do anything. So hopefully that merge code that you see here makes sense based on our merging back up, and the breakdown that we talked about here on the way down also makes sense. So hopefully you can match the algorithm to what you see here in the code. This is not the only good code that's around on the internet. You can find plenty more. And again, down here, I just have some code that lets the user type in some items and then sorts them and displays them. It's not exciting at all. But hopefully that is a good introduction to you to merge sorting and how recursion makes a pretty good use of this, right? Now you can also see, because it's a divide and conquer algorithm, we're not misusing the stack. This is perfectly good, right? We're never going to have all that many items on the stack at one time in terms of function calls, because we're breaking the problem down into half each time, so not too bad. Hopefully that all makes sense. So thanks for watching this video. Come back and we're going to look at a second algorithm. We're going to look at the quicksort. We'll compare it in terms of its complexity, and we'll talk about the fact that the quicksort is a good general purpose sort that generally will be, if you just need to pick one randomly, pick a sorting mechanism, the quicksort is probably the one that you would use as a go-to. So thanks for watching this video. Come back for the last one on quicksorting if you'd like.